Welcome to homework.
This is the answer to Chapter 14, problem number 33 from the Smith Organic Chemistry textbook. And this problem gives us two molecules as ball and stick models and asks us to determine how many proton NMR signals each molecule is going to have and how many carbon NMR signals each molecule is going to have. And so I think that the way to start this problem, as always when we're given a ball and stick model, is going to be to redraw this in skeletal form. Ball and stick models are very good for some things, but for the most part, they are very difficult to work with, in my opinion. And I like skeletal models much more. So I've redrawn each of these here. And so in order to determine how many proton signals each of these molecules is going to have, we need to determine how many unique types of hydrogens there are in each molecule. And then likewise, in order to determine how many carbon NMR signals each molecule will give rise to, we need to determine how many unique carbons there are in each molecule. So looking at molecule A, these two protons are going to be equivalent, and so they're going to give us one signal. The 6 protons that are part of these two methyl groups are going to be equivalent. They're going to give us a second type of signal. These two protons here, as part of this methylene group, are equivalent and will give us a third signal. And then the 3 protons of this methyl group are equivalent and will give us a fourth signal. So we're going to have 4 proton NMR signals for molecule A. And then considering carbon signals, the carbon signals sort of roughly mirror the proton signals. So these 2 protons that I bracketed in black, they're on a single carbon. So this carbon here, that'll give us one type of signal. The carbons that are part of these 2 methyl groups here are going to give us a second carbon signal. Because again, remember, if their protons are equivalent, the carbons have to be equivalent too. And so this this carbon that had these 2 methylene protons, that's going to be a third unique carbon. And then this carbon from the methyl group at the end is going to be a fourth unique carbon. But we also have this 5th type of carbon in here, this tertiary carbon that doesn't have any protons on it, but it is going to give us a carbon NMR signal. And so we're going to have 5 13C NMR signals for molecule A. So then for molecule B, we'll do exactly the same thing. And so we have a methyl group here. So these protons are going to be one type of proton, so one signal. These 2 protons will be another signal. These 2 protons will be another signal. These 2 protons will be another signal. And then so I'm gonna switch back to black. I only have 4 colors to work with here. But you should not assume that this means that they're going to be the same as the other black protons. So these 2 protons are going to be a 5th type of signal. And then this methyl group at the end, these 3 protons are going to be a 6th type of signal. And so we're going to have 6 proton NMR signals for molecule B. So 6 HNMR signals. And then, again, we'll do the exact same thing with the carbons. So this carbon is unique. This carbon is unique. This one's unique. This one's unique. And this one. And so, again, we have a carbon that is unique, but that doesn't have any protons on it. And so that's this carbonyl carbon. And so that's going to give us a carbon NMR signal as well. And so when we count all these up, we have 7 different types of carbons here. So we're going to have 7 CNMR signals. Okay, and so that's the way to approach this problem. We just need to determine how many unique protons we have in each molecule to determine the number of proton NMR signals. And then we need to do the same thing for carbons. How many unique carbons do we have in each molecule? And that will tell us the number of carbon NMR signals. And that's the answer to chapter 14, problem number 33.